Hi students, welcome back. Today we will be discussing the topic of acidification of urine and renal regulation of acid-base balance. Now, we all know that regulation of hydrogen ions in the extracellular fluid is very important, as all the major activities of the body are taking place because of the presence of hydrogen ions. So, we need a proper control of hydrogen ion concentration in our body, and this hydrogen ion concentration in the body in ECF is somewhere around 0.004 milliequivalents per liter. Now this concentration of hydrogen ion should be maintained properly, and this is basically done by the 3' systems which are functioning in our body to maintain a pH of around 7.4. Alright, so the 3 primary mechanisms which control the concentration of hydrogen ions and keep them at a regular level so that the body homeostasis can be maintained are the buffers, the respiratory system, and the renal system. Now, buffers refer to the substances which are basically chemicals, and they tie up the hydrogen ions whenever hydrogen ion is in excess. They react within fraction of seconds and control hydrogen ion concentration. The buffers are present intracellularly as well as extracellularly. Now, the second role is of the respiratory system, which starts acting in few seconds after there is a change in the hydrogen ion concentration. And the basic mechanism through which the respiratory system is functioning is by capturing the hydrogen ion and converting it into carbonic acid, which is ultimately exhaled out as CO2 and water. Third, but not the least, last but not the least, the most effective mechanism is the renal mechanism, which tries to eliminate all the excess hydrogen ions and maintain acid-base balance. So, buffers starts acting within a fraction of seconds, respiratory systems comes into action in few seconds, and the renal mechanisms removes the excess hydrogen ion over a long period of time, but it is the most efficient mechanism. Here, point to note is that these buffers are not eliminating the hydrogen ion, they are just tying up the hydrogen ions. So, these are not efficient in removal of the hydrogen ion, only respiratory and renal mechanisms are efficient enough in the removal of the hydrogen ions. The acids can be volatile acids, or they can be non-volatile acids. Now, what do we mean by volatile and non-volatile acids? Volatile acids are those acids which generate hydrogen ion, and this hydrogen ions can be eliminated through the respiratory passage in form of H2CO3. So, the H ions which are obtained from bicarbonic acid, they can be eliminated by our respiratory tract through by forming of CO2 and H2O are referred to as the volatile acids. Rest are the acids which are produced as a result of metabolism in our body, and they cannot be eliminated by respiratory passage. They cannot be eliminated by the respiratory passage, are referred to as non-volatile acids. These non-volatile acids require renal excretion. So, mandatorily renal excretion is required for the elimination of non-volatile acids. So we can see. Now talking about secretion of hydrogen ion and reabsorption of bicarbonate ions. These phenomena are more prominent in the segments of proximal tubule, ascending thick loop of Henle and the distal tubule. To understand the process, let us see a tubular epithelial cell. This is the basolateral side of the tubular epithelial cell and this is the renal interstitium. This is the lumen with the luminal side. We all know that the basolateral side has a very important pump which is sodium potassium ATPase pump. It is a primary pump, and on the basolateral side one pump which is a secondary active pump is present, and this pump is sodium hydrogen counter port, as it pumps hydrogen out and sodium ions inside. Now because of the various metabolic processes inside the tubular epithelial cell, CO2 is produced, and this CO2 combines with water to form the carbonic acid in the presence of enzyme carbonic anhydrase. Now this carbonic acid dissociates to form the hydrogen ions as well as the bicarbonate ions. Now hydrogen ions produced like this needs to be removed out from the cell. So it moves out when the secondary active pump, which has got an energy driven by the primary active pump, removes hydrogen out of the cell with sodium ions being pumped in simultaneously. Now this hydrogen ions reaches the lumen, and in the lumen bicarbonate ions are present because bicarbonate is filtered across the glomerular epithelium barrier and it reaches into the tubular fluid. Now this bicarbonate combines with the hydrogen ion here to form again carbonic acid, and this carbonic acid again dissociates into H2O and CO2. Now this CO2 diffuses back, and finally the hydrogen ion which was removed combines with the bicarbonate ion which was present in the lumen. So the net effect of this complete reaction is that the bicarbonate which was in the lumen finally gets reabsorbed back as the bicarbonate, but this bicarbonate is not the same which is entering the renal interstitium from this side. But however, hydrogen ions are secreted out and bicarbonate are reabsorbed back. But the hydrogen ion, as you can see, they are not finally excreted because they are combining with the bicarbonate ions. So this net effect of this process, net effect is that bicarbonate is reabsorbed but hydrogen ion is not excreted out. So this mechanism is mainly important for the reabsorption of the bicarbonate ion without increasing the acidity of the urine. Alright, so we can say that as a result of this process, about 90% of the bicarbonates are reabsorbed back. And therefore, which is equivalent to the hydrogen ion which are secreted. I am here saying secreted, not excreted, and this amounts to somewhere around 3900 milli equivalents. So finally, reabsorption of bicarbonate occurs from the tubules, although bicarbonate which is entering is not the same molecule which was travelling in the lumen. Bicarbonate here which is entering is as a result of the dissociation of the carbonic acid, and the bicarbonate here in the lumen is again combining with the hydrogen ions to form the carbonic acid. So, but we can understand one thing from this complete mechanism, that whenever bicarbonate needs to be absorbed, it needs equal amount of hydrogen ion to be present in the lumen. Only then it can be absorbed. Otherwise, it will not be reabsorbed. Now, bicarbonate which is reabsorbed back, it follows either bicarbonate chloride exchanger or sodium bicarbonate transporter. Okay. Now, the other mechanism which is functioning in the late distal tubule and collecting duct for the absorption of bicarbonate and the secretion of hydrogen ion is involvement of hydrogen ion transporter. Now again, let's draw a tubular epithelial cell here. This is the intercalated cell. Which are present in late distal tubule and in the collecting duct. Now, we all know that CO2 produced because of the metabolic processes in the cell will produce carbonic acid, and this carbonic acid will dissociate to give rise to hydrogen ion and bicarbonate ion. These bicarbonate ion will move across the basolateral site and the hydrogen ion which is generated inside the tubular epithelial cell moves out across the luminal epithelium by utilizing a very active pump which is known as hydrogen ATPase transporting pump. It is an ATP driven pump, it is a primary pump, and it does not require the energy of the sodium potassium pump which is operating at the basolateral membrane. So, this is hydrogen ATPase transporter. So, hydrogen ion in the late distal tubule occur by utilizing hydrogen ATPase transporter which is a primary pump. Although the secretion of hydrogen ion here in this segment is merely 5% as compared to hydrogen ion secretion in the earlier segment which was somewhere around 90%. This 5% of hydrogen ion secreted in this segment contributes to the formation of maximally acidic urine. As we can see here, the hydrogen ion is not getting reabsorbed back. But in the earlier segments, the hydrogen ion combined with the bicarbonate and it was getting reabsorbed back. Thus, the acidity of the luminal fluid was not increasing. But as the tubular fluid reaches the late distal tubule and the collecting tubules, the hydrogen which gets secreted here does not get any bicarbonate and therefore it increases the acidity of the tubular fluid. So, 5% hydrogen ion providing maximum acidic urine here, and as a result of which the pH of tubular fluid reaches to somewhere around 4.5. Now, this 4.5 pH is the limiting pH which can be tolerated by the tubular epithelial cells. Limiting pH which can be tolerated by the tubular epithelial cells. Right. Now, this hydrogen ion which combines with the bicarbonate ion does not harm the tubular epithelial cell, but the remaining hydrogen ion which are getting secreted in ionic form, hydrogen ions in ionic form cannot be excreted as such because they will cause damage to the tubular epithelial cells. Therefore, for removal of such hydrogen ions, buffers are required to neutralize the effect of hydrogen ion. As we have seen earlier that 4320 milliequivalents of hydrogen ion was getting excreted in conjunction with bicarbonate. Remaining 80 milliequivalents of hydrogen ions require buffers so as to neutralize the effect of the acidity and so that they can be removed easily by the renal system. Because we can see that the limiting pH is 4.5, so that means a hydrogen ion concentration at this pH would be 10 raised to power minus 4.5, which will be somewhere around 0.03 milliequivalents per liter. Thus, we can say that for 1 liter urine, only 0.03 milliequivalents of hydrogen ions can be excreted. But the body has to excrete 80 milliequivalents. So, to remove these 80 milliequivalents, large amount of urine would be required, somewhere around 2667 liters, which is practically not possible. So, with the limiting pH of 4.5 and excretion of hydrogen ion limited to 0.03 milliequivalents in 1 liter, body needs the buffers. The renal system require buffers to remove these excess of hydrogen ions. So, what are these buffers? Let's see these buffers one by one. Buffers in renal system. Two major buffers are present. One is the phosphate buffer and other is the ammonia buffer. Let's talk about phosphate buffer first. Which consists of HPO4 and H2PO4. Now these phosphates, hydrogen phosphates and dihydrogen phosphates are present in excess quantities in the tubular lumen because they are not reabsorbed back and they get concentrated towards the distal tubular segments. Now let us see how these buffers are acting by drawing a diagram of the tubular epithelial cell. Here is the sodium potassium pump at the basolateral membrane. This is the tubular lumen. This is the luminal surface. We all know that metabolic processes in the cell produces CO2 and this CO2 will combine with water to produce carbonic acid. And as a result of dissociation of carbonic acid, bicarbonate and hydrogen ion are produced. All this is occurring in the presence of enzyme carbonic anhydrase, which accelerates the process. Now, bicarbonate will diffuse out from the basolateral site and reaches the renal interstitium, thus adding up to the bicarbonate bank of the body. On the other hand, what is happening here that phosphates are present in the lumen. This hydrogen phosphate, monophosphate, combines with the hydrogen ion which is secreted across the luminal surface because of the activity of sodium hydrogen counterport. Now this hydrogen ion combines with the hydrogen phosphate to form dihydrogen phosphate ion. This basically happens and this dihydrogen phosphate ion combines with the sodium ion which is present in the lumen to form sodium dihydrogen phosphate, and this sodium dihydrogen phosphate is excreted out in urine. Now we can clearly see from this chart that the hydrogen ion which are generated inside the body or inside the cell are finally excreted out of the body by combining them with a buffer, and as a result of which excess of hydrogen ion which are to be eliminated are easily eliminated without providing any harm to the luminal epithelium, because the buffers are tying up the hydrogen ions and thus trying to remove as much as hydrogen ion as well as maintaining the pH of the luminal fluid. Now this phosphate buffer has a pK range of about 6.8 and it is one of the most effective buffer in the renal system, which is eliminating hydrogen ion because its pK is close to the pH of the tubular fluid. Alright, now moving on to the next buffer, which is the ammonia buffer. Ammonia buffer is most important quantitatively. So it is more important as it removes large amount of hydrogen ion. The pK of the ammonia buffer system is lying somewhere around 9. So it is not so efficient as compared to the phosphate buffer, but quantitatively it removes more hydrogen ion as compared to the phosphate buffer system. Let us draw a diagram of tubular epithelial cell to understand the functioning of the ammonia buffer. Ammonia buffer requires the presence of ammonia and ammonium ions. Now, ammonia is generated inside the epithelial cell by breakdown of glutamine. Glutamine causes release of the ammonium ions, and along with that 2 bicarbonates are produced. However, in the collecting tubule, the mechanism is somewhat different, which involves directly diffusion of the ammonium ions from the tubular epithelial cell into the lumen. This is the lumen, and what happens? These ammonium ion diffuses out of the luminal side because of the presence of sodium ammonium ion counterport. This is the basolateral surface where we have functioning sodium potassium ATPase pump. And ammonia CO2 produced in the cell forms H2CO3, producing hydrogen ion and bicarbonate ions. And finally, this hydrogen ion is getting removed because glutamine was initially producing NH3, and this NH3 combines with the hydrogen ion to form the ammonium ion, and this ammonium ion is excreted out and is removed from the body and it is excreted. Now the phenomena is somewhat different, as I told you, in the collecting tubules, where this is the tubular epithelial cell. CO2 is producing H2CO3, and this H2CO3 forms the bicarbonate as well as hydrogen ion, and this hydrogen ion moves out in the because of the presence of hydrogen ATPase transporter, and once it reaches the lumen, it combines with the ammonia which diffuses out of the tubular epithelium. Now this ammonia combines with the hydrogen ion to form the ammonium ions, which are finally excreted out. And this bicarbonate enters the renal interstitium and adds to the bicarbonate pool of the extracellular fluid. So we can see in both the conditions, whenever the phosphate buffer is functioning or whether the ammonia buffer is functioning, there is actual removal of the hydrogen ion which is excreted in the urine, and moreover there is addition of a bicarbonate ion to the pool of the body. So this addition of bicarbonate ion along with excretion of the new excretion of the hydrogen ion is very important for maintaining the pH of the tubular fluid as well as maintaining the pH of the urinary system. Now this bicarbonate which are added to the body are referred to as neobicarbonates, because they are not the bicarbonates which were traveling in the lumen, but they are new bicarbonate which are generated inside the tubular epithelial cells along with the removal of the hydrogen ion. So please remember, neobicarbonate production occurs only with the action of the buffers, and they are not produced by the action of the bicarbonate reabsorption. When bicarbonate reabsorption was occurring along with the hydrogen ion secretion, then the bicarbonate which was added in the previous section, this bicarbonate which was added was not the new bicarbonate. It was not a new generated bicarbonate. It was somehow the luminal bicarbonate was we consider it to be getting reabsorbed. But here in the phosphate buffer and the ammonia buffer system, the bicarbonate which is getting added up is a new bicarbonate. So this accounts for the increasing the hydrogen excretion as well as maintaining the bicarbonate reserve of the body. Now to quantify the how much amount of acid is getting secreted, we can say that net acid secretion excretion by the renal system is equivalent to amount of ammonium ions which are getting excreted plus urinary titrable acid minus bicarbonate excretion. Minus the bicarbonate excretion. Now, how do we calculate the urinary titrable acid? Another important thing here is to know the urinary titrable acid. First of all, let us be clear what is ammonia ions excreted. As we have seen in our previous section that the buffer, ammonia buffer, ammonium ion buffer was combining with the hydrogen ion, and the amount of hydrogen ion which this ammonium buffer was combining leads to loss of this hydrogen ion in the urine, and as a result of which the hydrogen ion can be measured by measuring the total amount of ammonium ion which are excreted in the urine. Now, titrable acid refers to non-ammonium, non-bicarbonate hydrogen ions. That means those hydrogen ions which are generated and are released and are excreted into the urine and are not combined to the ammonium buffer, but they are present as hydrogen ion in the urine, and they can be titrated by adding sodium hydroxide to a sample of urine to bring back the acidity or the pH of the urine to somewhere around 7.4. So, the amount of sodium hydroxide which is needed to bring back the pH to 7.4 will account for non-ammonium, non-bicarbonate hydrogen ions, and this is what is known as titrable acidity. Okay. Another thing which you need to know is that amount of neobicarbonate added. To body is equivalent amount of hydrogen ion lost, and this loss can be either because of ammonium ion buffer or the phosphate ion buffer or the phosphate buffer. Now, ammonium buffer is the amount of ammonia excreted, and phosphate buffer can be known by knowing the titrable acidity. This is all for acid-base buffer system. Thank you.